Hi everyone, this is Analog Circuit Design, Lecture 16, Current Mirror. I'm Theo Kang.
I would like to acknowledge my advisor Michael Flynn and my friend Sung Jong Lee for his feedback. Here's the outline. We'll learn about what the current mirror is and its very basic structure. Current source biasing, why important? A lot of analog circuits need current source, especially amplifier. Most of the amplifier use current source, but some of them are not, but most of them. For example, source follower, here there's an input device NMOS, and then current source is attached here, and then we see the V out. The very basic form was this. There was resistor and V out. But this is better because the resistor, to make an amplifier, we need to set the DC current, and also we need to set the small signal gain. But if you use just RS, where the small signal gain and then the large signal resistance are the same, so we don't have much, like it's kind of hard to set the operation region at the same time with the gain. Also, this RS is not good for linearity for this whole overall circuit, because if you change V in, this voltage changes a lot because of this RS. So like the gain changes depends on V in. But if you change it to this current source, it's better. It is at a very stable DC current, and then it offers a high output resistance. Well, the gain is here almost 1, and it has better linearity. So current source also use the source follower use current source, and then the cascade. The upper one is actually a current source. So this is the same as, we can also represent it as like this. So we also need this current source in cascade and differential pair. So we haven't learned this yet. This is differential. So the amplifier, you see that the input, there are 2 input and then output. So it works as differential, but for that we need this current source. So in this case, this is current source. And in the differential amplifier, this current source plays an important role. So overall, the current source is really important. So the current source is used very widely. The other part of the important point is we need to control the current value. So we want to control the current value like very well. We want the current value is defined very properly, like 10 micro or 20 micro. So what we do is we have a reference generator. This is like golden reference, like very accurate reference. Let's just assume that we have this. So for example, in industry, we calibrate this IREF. So you know the calibrate means that we calibrate the IREF. So calibration means that we want to set that value accurately. So once chip is fabricated, we measured it, and then we tune it, like using maybe some resistor tree and digital input. So we calibrate it. So we do have a very accurate current reference, let's say 10 microamp or something. And then what we do is we use a single current source and then copy it to other parts. So here we have one fixed current source and copy it to other parts of the circuit. And then maybe the other question may arise that why do we have to copy? Can we just have multiple I reference? Can we just have multiple golden reference? Yes, we can. It's just expensive. If we have multiple golden references, which means that we have to calibrate all of them. Those golden references usually have larger area in terms of layout, but that's kind of fine. But the more problem is that the calibration. We cannot do calibration over lots of current sources. It's because it takes a lot of time, and then time means cost. So usually we cannot have lots of IREF. We can have so maybe we can just write it down there. We cannot have many IREF due to cost. Well, I'll say calibration cost. So that's why we need to copy. We need to just have one single and then want to copy it. So what does this copying circuit looks like? So it would be like this. We have a golden reference here, and then there's some copy circuit, and then we will learn about this today. And then this will generate some gate voltage, and this NMOS will operate as a current source. A very simple way to that we can think of is by using this circuit. So in the previous slide, what we want was there was IREF and some mirror circuit and like this, right? So in this case, IREF corresponds to VDD R1 plus R2. And then this I out can be represented as this equation. Well, let's just ignore channel length modulation. So it's a VGS, right? But this is not good. We cannot use this circuit because of the PVT dependencies. PVT means P, process, V, supply voltage, T, temperature. So process means like TT, SS, or FF. So it's about like NMOS and PMOS performance. TT means both of them are normal, typical. SS means NMOS and PMOS are slow. FF means fast. So slow means, so one thing of this slow is VTH is high. FF, VTH is low. So the process is defined when we make a chip. So it depends on like each die. It will not change it. So once the chip is fabricated, this process is fixed. And so what it says is because of this VTH is variable, because of this process variance, we cannot have a constant I out, right? But how about and then the supply voltage, this is also a problem. Supply voltage means VDD, it means a VDD variance. So usually in industry, typically for 1 volt, we see like minus 5% and 1.0 and then 1.05 volt. So these 3 voltages are also used in industry. We assume that the supply voltage can change we don't assume supply voltage is a constant. We assume that these things, and this circuit has to operate well over these variance. But when we see the current, the VDD is here, so this is not a constant. So it gives us a variance on I out. So it's not good, because what we want is we want I out a constant, a function of I ref. And then temperature. So temperature is related to this VTH, and then mu and Cox too. But the VTH is a key component for that. So if temperature changes, we cannot copy this IRF. So we cannot use this circuit because these are too it's vulnerable to PVT variation. So we need better circuit to replicate this IREF. So what we discussed was IREF in the previous slide. We need some circuit like this, and we're going to use this diode connected NMOS, and that's what we call the current mirror. This is actually the basic structure of current mirror. So let's see how it works. First, VGS1 is set to support IREF through M1. Assuming that we have a very strong current source, then this M1 must flow this IREF. And you see that the current will be, for M1, IREF is 1/2 mu n Cox. It means that M1 W/L, then VGS1 minus VTH square. Let's ignore the channel length modulation at this point. Then we can solve this equation over this VGS1, right? And then that VGS1 is set by this IREF. And then, so we made this circuit. We made this voltage, and then this voltage goes to here. So VGS1 is applied to the gate of M2. If we assume that the M2 also has a same W/L, then the current flow will be I out will be the same as I ref if W/L1 equal W/L2, right? If we assume there's no channel length modulation. Again, if there's no channel length modulation, that means that the current of the MOSFET is only defined by VGS, right? So this will happen. And then, by the way, here we use diode connected FET. Diode connected. So it guarantees the saturation of on M1, right? Because the saturation condition was VGS1 minus VT. Well, let's just remove VGS. I say VGS minus VTH should be smaller than VDS, right? But for the diode connection, this VGS and VDS are the same, so this equation always met. So there's a few things that we can think about. First, the ratio of W/L sets the current ratio. So what it says is I1 and because M1, let's say M1 is 1/2 mu n x W/L1 and VGS1 minus VTH square, right? How about I2, which is I out, in this case, which is I ref. So I2 will be same, mu n Cox, but in this case, it will be W/2, L over, and then 2. And this is the same, so since they have a same gate voltage. So if we just divide it, then it will be WL1, WL2. And the other thing would be if Vx tracks for mu, Vx tracks for mu n and VTH variations. So, so here's the assumption. Assumption would be Iref is constant. So if Iref is constant, because of this equation, this VGS1 will track, which is Vx, so Vx means here. So here's x, and the Vx is VGS1. So VGS1 tracks for mu n or VTH variations, because in previous slide we talked about PVT variation, but now since we have a golden current source, this like force this M1 to flow this Iref. So if these values are changing, then VGS1 has to track them. And again, the assumption is Iref is constant. And well, this assumption is correct because this Iref is kind of special circuit, and we also do a calibration. So we can assume this Iref is constant at this moment. And the third one, this is also important. We set L1 and L2 the same. This is because here we talked about that the ratio between this Iref and I out here can be controlled by the ratio between W over L1, W over L2, right? So if we want to change this ratio, we can change either L or W for each MOSFET. But we always set L1 and L2 the same. We'll discuss it in next slides. Let's see why we have to set the length the same and size W to set the current ratio. So in the previous slide, what we talked was, so Iref and I out, the ratio was the ratio between W W over L over W over L2, right? So one is, well, here this transistor, and then 2 is the target transistor. And the reason for setting the transistor the same is here, the first reason is that minimize the error from side diffusion. So LD. So L effective is L drawn minus 2LD. So what it means is when we draw transistor, so this is L drawn. And L effective is here. This is L effective. And this little tiny part, is L diffusion. So it's hard to predict the exact L effective because what we can control is L drone. L drone means when we do layout, like the layout will look like this. So this will be the gate and this will be the L. So we can control this L drone. So this is L drone. Literally we drew the L, so that's why we call it L drone. We can control this value, but we cannot control L effective because it's really hard to predict. So when we double let's say if you want to control the current ratio by changing L, so assuming that, okay, so we want to make it like half current by doubling L drone. In this case, we draw L drone double. Okay, we want to, in this case, let's say we want to double this like here. So we make this L 2L drone. So we can control that, but we don't know about this LD. So the L effective prime is not this is not L effective, 2L effective, right? Let me just, so this is L effective new, but this is not 2L effective. So that's the point, because we cannot predict this LD. And then the other one is that VTH is also VTH also depends on the length of short channel devices. So for like advanced technology, or when L is not that big, VTH changes over this length. So it's better. In most of the case, set the length as a constant over 2 current mirror. And there's the other thing too. Okay, so now we understand. Now we get that. Okay, we have to set the length the same. Then the other thing that we can do is sizing W, right? But there's multiple ways to size W. First, the most intuitive way maybe we can think of is just doubling the width. What I'm saying is, in terms of layout, let's say we have this transistor, and then we want to make the current double. Then what we can do is, well, maybe this is too large. So we have a transistor like this, and W is here, right? So because we want to, let's say we want to double the current, then we can double this W, right? And this is 2W, which is shown in this case, this example. But the problem is, this will not give us exact double current. And the reason is here, and then, so when we see the W, that's kind of similar with this. You see that this corner, we have some irregularity. I mean, it's not like constant, not very regular, because you see this corner, like here, some gap here, and then the angle is different. So doubling doesn't mean that, just purely doubling this will not give us exact effective double width. So we don't do this, we don't do that. Then, so there's total 3-way. First one is just double width. It's not that good. The second one is using finger 2. Well, this is better than this one, because fingering was here. This is fingering, okay? So the W is kept the same, but we just increase the finger. But this is also not that accurate. It's better than this number 1 option, which is here. But fingering also is not perfectly duplicating, perfectly doubling the MOSFET, because you see, usually it's like here base, source, and drain, and we have to connect these two like using metal. So they are better than just using 2W, double width, but it's still not perfect. So we can use number 3 would be multiply. Mult 2. So this is different, and this shows that. So mult 2 is this. We're literally just using an exact same MOSFET twice. So it will be like 1, and 2. So this would be M2. And this gives us a better result, better matching, like better ratio. But the cons for this is that it will consume more area. You see that if you just use finger 2, then they're sharing source, so we can save area. But if you don't use finger, just by using M, then it consumes more area. So area issue. And then because there's a lot of layout rule, so you have to put some space here. So just using M2 is not good in terms of area, but if you really need an accurate current matching, then this is the way to go. And then if you don't need that much of accuracy on current ratio, then maybe you can go for this finger 2. I brought this figure from a Zabi book. This is very obvious. If you think this is obvious, then it means that you understand it like well. So what it says is, first here, what we need is, so our target was IREF. There was IREF. And then we need some circuit that can kind of replicate this IREF and I out from IREF. So if you see this example, this circuit cannot copy the current. So it means that by using this, and we can just assume that this is, let's say this is just voltage source, okay? Just voltage source. We put some voltage source, and this is not working because this voltage has nothing to do with this IREF, right? Because this gate of the MOSFET is input, not output. So we need something, we need some path that that makes this gate voltage as a function of IREF. So this will not work. And then if we come back here, so this is what we discussed, that the diode connection of NMOS over this IREF. So now we got this voltage is now is function of IREF, right? Because IREF goes here, and then this will automatically set the voltage here. Let's think about it in this way. So in terms of like timeline, okay? I mean in transient point of view. And then assuming that we have some C, some cap, because it's let's say parasitic cap here, and assuming that this voltage, and here's IREF, and this voltage is, let's say, VGS. So if you see in the time domain, and here's IREF, let's say ID1, and here is VGS. So at the very beginning, let's say ID1 is 0, and then we increase ID1 to IREF. If the current is 0, assuming that the start of the VGS is 0, okay? So here is 0 and 0. Once the current starts to flow, this voltage here will go up, and it will settle at the VGS1, that our target, like, because here the reason why the voltage goes up, the voltage increase, is that when VGS is 0, let's say this voltage is 0, this MOSFET is turned off, right? If this is turned off, the current has to flow to this capacitor, right? So if since the current flows here, so the current flows here first, that's why the voltage increases. But since the voltage increases here, this MOSFET starts to flow the current. So the current flow here will decrease, and once this MOSFET is like turned on enough to flow this IREF, this current will disappear. I mean, this current will never will not once this ID1 reaches the IREF, then this current will, well, actually, let me just rephrase this. So this one should be IREF. Let's say this is ID1, and IREF, and so this will be ID1, and this is let's say C. So ID1 is not going to IREF immediately. It's also increased like this, and then it finally goes to IREF, and at the same time IC, the current that flows to the capacitor IC. At first this starts from IREF, but it degrades like this to 0. So again, here the point is that at the initial condition, if this IREF start to flow, since the MOSFET at the beginning is turned off, so current will flow this parasitic capacitance. Hence, this gate voltage goes up, and then this NMOS starts to flow the current. And once this NMOS current is equal to IREF, then the current flow to capacitor stops, and then the voltage settles. Let's see the problem set from Razavi book. The problem set is about calculate the small signal voltage gain. This is not current gain, voltage gain from this circuit. So let's say this is ID1 and then this is ID3. So if we change Vin, then the delta ID1 is okay. So the delta ID1 is GM delta Vin, right? And what about ID3? So delta ID3 would be the ratio between these, because these are current mirror, right? So the delta ID3 would be the delta ID2, delta ID1 times the ratio 2, right? Because those are from here. Well, note that delta ID1 is delta ID2 because they're in the same branch. And then the output would be the Vout. Delta Vout is delta ID3 times RL. And what about the polarity? Polarity is plus, so look at this. If we increase Vin, if we increase, assuming that we increase V in, ID1 increases, right? If ID1 increases, because of this current mirror, ID3 also increases. ID3 also increases. If ID3 increases, the V out is the current times RL. So the polarity is plus. Also, we can also think of it like this is a CS common source amplifier. So common source amplifier, the voltage gain is negative. And then we got another common source amplifier because this is PMOS. So the gain from here to here is also negative. So negative times negative is positive. So it turns out V out is delta ID3, which is ID1 times the ratio between resistor to transistor, and then ID1 is GM in times this ratio. So overall, the voltage gain is V, which is delta V in and delta V out, which is GM RL, so this is L, times the ratio between transistors. Let me talk about some side story. The current mirror in commercial chip, which means industry, like in industry. So it looks like this. There's a lot of current source array, and we call this block as a current bias block. So we have this, and then we have a block, like schematic block like this, and then these are ports. Okay, these are some ports, and we have a like current reference, like IREF, and maybe it goes to like this, something like this. And then people usually call this as I bias block. And let's say this whole space is a chip, like the layout, and then let's say here is some like ADC, or maybe here is some mixer, or here some DAC, and there is a main current bias block, and then this block provides this current source to here or there, or maybe this ADC requires use two current source, and this mixer use one current source. So this is how like the one way to implement this I bias. So the point here is that there is a current bias block, and then this block uses current mirror here, and then this can be maybe 10 microamp, this can be 5 microamp, this can be 5 microamp, or a bunch of current value here. And the center I bias block provides the current to like multiple circuit that needs some current. So the current bias are all in a same area. Like we cannot put. So the point that I want to say is we cannot put like current source here. Like let's say current source is here. So we're just taking. We can also think that, oh, we can just take this voltage to here, right? And then here's the voltage. No, we are not doing it. So the current source should be very close, very proximate to the main current branch. We call this as branch. So they have to be in the same area, like very near. The distance is important because to make this current mirror, what we learned is their current ratio is decided by this ratio, right? And also like VTH or mu n COX or mu p COX, which is for PMOS. So these variables are important, and then these variables should be aligned between these branches. And these variations are strong function of distance. If saying if the distance between this and this is far, is very long, then it's highly likely that they are not matched. So they should be very close. Like this should be distance should be small. They should be very close, so they can perfectly match the replicate the current. So that's why there's usually a common the main current bias block, and they provide multiple currents. And like some engineer only take charge in this I bias, and then the engineer of this I bias communicate with other blocks people. We call this as DRI, which means directly responsible individuals. It's like a owner of this block. So the DRI of iBias, I mean the owner of iBias, communicate with the owner of mixer, the owner of ADC, the owner of DAC, and then these circuit guys ask iBias, oh, I need 10 micro, 5 micro, 20 micro, and then this iBias guy provide this current. So far, we assume that there's no channel length modulation, but that's not the real case, right? We do have to consider channel length modulations, and let's bring up this same circuit, but now the current is this. You see that now we see this channel length modulation. So the ratio between them is not anymore the ratio of this dimension, but we also see this one. So we see this. To align these two, we need to set VDS1 and VDS2 the same, which means here is VDS1, which is also same as VGS1, and this is VDS2. So if those two are not the same voltage, the currents are not properly ratioed. It says the ratio are not accurate. Well, there's one way that we can mitigate this impact. So that could be if we use longer L. Well, and as I said, this is L is same for both M1 and M2, right? If we use longer L, large L, lambda is decreasing. So maybe less current error. But there's the other way. I mean, this is also a good way to do it. And usually when people design a current source, we use a long L. But we can also improve this in circuit-wise. To mitigate the current ratio error from channel length modulation, we're going to use cascode. The cascode current mirror is that we will add one more NMOS, and we set some voltage, which is VB. I will talk about it later, how to set this VB. So if we set here, then um, this here is x, and then let's if this is y. We can set somehow, like by choosing VB properly, then we can fix Vy and Vx kind of same, so we can match the current more accurately. We can overcome the channel length modulation. So our goal is to set VB properly, so Vx can be Vy. And as we learned about Cascode, from Cascode, the advantage of Cascode is that here, VP, if the voltage here, VP changed like this, then the voltage change at Vy is mitigated. So this is good because if there's some circuit and then the circuit changes the voltage here a lot, this M3 MOSFET blocks the voltage change, and then this Y will stay still. So it's like voltage change Vy is a lot less than voltage change Vp. And again, our problem is that how to set this Vb, right? So our target was to set this bias here, Vb. One way to do it is double cascode. We add this M0 here. So the top mirror generates Vb for B3. This top mirror means M0. And as a second mirror on top of M1 and M2 mirror. So these are second mirror, M0 and M3. So here. And the sizing follows the ratio between here. So M1 to M2, the ratio between M1 to M2 should be equal to M0 and M3 ratio. So how does it work? As M1 and M2, there is VGS1. They set it, and so VGS1 is equal to VGS2, right? And then M0 and M3 should flow like a similar current. So VGS0 is kind of equal to VGS3 because these two also should flow the same current. Well, there is a channel length modulation, but channel length modulation is not like a major, it's not like huge contribution to the current. I mean, they do contribute the current, but still the VGS is more the main cause. So VGS 0 and then VGS 3 should be similar, which means that Vx and Vi should go similar. And again, the advantage of this part is that the voltage change here at P will be mitigated to Y. So these two are operate as a perfect good, like a shelter for this voltage Y. So this cascode current mirror is good in terms of like mitigating channel length modulation, but it has a problem, headroom problem. The assumption is that every transistor should be in saturation region. This is a must condition. To do that, let's say this is VGS1, and here is VGS1 plus VGS2, right? VGS0, because here is VGS0, which means this voltage, the VP has to be larger than VGS1 plus VGS0 minus VTH, well, 3. Let's say VTH. So this is our like condition. it says, let's say this is VTH3, and maybe we can assume like, let's bring up some actual number. Let's say VOV is like 200 millivolt, just in case. And then VTH, I mean, for example, and then VTH, like 400 millivolt. And this turns out, VP should be larger than, so this is actually, it's kind of similar to VGS1 minus VTH1 plus VGS0 minus VTH3 plus VTH1, right? I mean they're the same. This is the same, so we can kind of approximate 2 VOV because this is VOV. 2 VOV plus VTH, and it turns out like 800 millivolt. So VP has to larger than 800 millivolt, assuming that our supply voltage is like 1.8 volt. 1.8. We can only use this part, and usually this is not a good usage of our domain, because like almost half of the VDD we cannot utilize it. So this is a problem. So we now need some different approach. Before moving on to the next current meter circuit, let's look at the DC operating points further for this cascode current meter circuit. What we're going to do is that we will sweep the voltage here and then see how the operation region of M2 and M3 change. So I brought this example is from Razabi, and I would say it's kind of confusing. They say like VGS3. It's not like what's the VGS3 are they talking about? I think they try to say VGS0, and also here VDS3. This is also like VDS is a function of VX, so it's not like too natural to put this VDS3 at this point. But the thing that we can get from it is that we want to see how's the operation region change. Let's say if Vx is like high, then both of them are in saturation, right? Because the assumption of saturation region is that the VDS should be high enough than VGS minus VTH. And if we decrease Vx, and then we need to figure out which NMOS will go triode, go linear first. I think that's the key point of this example. So the answer is M3 will go to linear region first, and M2 will stay in saturation further. Because here, that's because VB is not changing much, while Vx changes more. So VB is kind of stays still, so that's why this transistor will stay at the region that they stay, but for this transistor, Vx is changing, so their operation region breaks first. And then also assume that if we can think of it the other way too. Let's say M2 will go linear first. That means this VB will be smaller than VGS. Let's say VA minus VTH2. So if that voltage goes low, then it goes to linear, right? But that doesn't make sense, because if this voltage goes low, in terms of this transistor, the VGS becomes really large. So the current from this area should increase. So, but since this is going to linear, then the current should decrease in this part. So that doesn't make sense. So the M3 will go linear first. And then if Vx is really small, then both of them are in linear region. And then we can also think about, like, what if Vx is too large? What would happen? Like Vx is really large. Then what happens is M2 M2 is still stays in saturation, but M3 will turn off. Because if we increase this voltage, VB should increase too, right? The VB is increasing, and then eventually the VGS3 will be less than VTH. So M3 will, like, kind of in off region, but since the VDS is too large, it still flows the current. Well, I mean, it's not important about thinking of too large Vx, so you can just forget about it if you are not clear about that. But anyway, the point here is that if we decrease Vx, M3 will go linear first. Next, let's see some further circuits, because in cascade mirror, we have a voltage headroom issue. So here's a headroom issue. So we will see several techniques that can overcome the headroom issue. To improve circuit, we have to see that it's even possible. Do we even have a room for improving the voltage headroom? What I'm saying is, so we need this. So this is mandatory. This is must, because we are going to use this cascade because it has some advantage that protects this voltage of Y from outside. So the current is matched, aligned better even with channel length modulation. So this is must. This is our assumption. And we want to see that can we change this voltage N. So our goal is reduce Vn. That's our goal. In our current mirror, Vn is VGS1 plus VGS0, right? Because here is VGS1 and then here is VGS2, VGS0. So because of this, Vp should be larger than Vn minus VTH3, which is around 2 VOV minus VTH. Okay, so here this is our condition, our current status. But let's see the circuit again. Let's see the diode connection first. So diode connection is not like optimum connection in terms of saturation mode, because the saturation mode condition is VDS should be larger than VGS minus VTH, right? But in diode connection, VDS is equal to VGS. That's the diode connection provides. And now we're missing this VTH. So VDS it doesn't have to be VGS. It can be lower by VTH. So we're kind of wasting this amount of voltage in diode connection. So when we also see the two stacked MOSFET, we're going to find out what's the minimum voltage that we can have. So assuming that we have VGS 0 and then VGS 1. So let's see this voltage. Let's say this is X. So Vx, the minimum Vx is VGS 0 minus VTH 0, right? And here, N. The minimum Vn should be VGS. So minimum Vn should be larger than Vx plus VGS1, right? Because this voltage represents here, okay? This part. Because here is Vx plus VGS1 minus VTH 0. Oh, sorry, so this should be VTH1 because this is M1 and this is M0. So technically, if we combine these two, Vn can be as low as, we can just substitute that, VGS0 plus VGS1 minus VTH 0 minus VTH1, which is like around 2 VOV. So can you see the difference? This 2 VOV is the minimum value that we can achieve. So compared to our current mirror case, cascode current mirror case, we can save VTH. So it's like the conclusion is that we can save VTH in headroom, and this is our goal to save. As we discussed in the previous slide, we can improve, our goal is improve headroom by VTH. And it turns out the only way that we can do is we need to reduce this voltage, this VDS1. In the diode connected version, VDS1 was in a diode connected, cascode current mirror, the first structure. VGS1 was VDS1, but this is not what we want. We don't want it. We don't want it because of headroom issue. So we need to do some other, we need to use some other circuit that can make VDS1 is equal to VGS1 minus VTH. This is what we need. We need to find some circuit that can generate this. And if that's possible, then we can also set VB. We need VB to some value. So what it means is that, assuming that we achieve this, that means our goal is to set this as VGS1 minus VTH1. Well, let's just say VTH. So we can set this, and then VB turns out VGS1 plus VGS3 minus VTH, right? So this is our also goal. Our goal is our target VB. So target VB becomes this, and then this can make our VP as VB minus VTH, which is 2 VOV, right? So this is our the thinking flow. Since we figured out in the previous slide that we can improve headroom by VTH, and the only way to do that is we need to reduce the voltage here. Not using diode connection, we need some other circuit, so we can reduce this VDS to VGS1 minus VTH. So in diode connected, it was just same. VGS and VDS was same because it's diode connected. But we need to do something to make VDS low. And since VDS becomes low, we can make Y, the voltage Y, lower. Like we can set it like this. And then to do so, we need this target VB. So actually, so this target VB can satisfy this Y voltage. So our target VB becomes this, which is VTH lower than the previous cascode current mirror. By doing so, we can improve VP to the minimum VP to 2 VOV, which means we can improve the headroom by VTH. So that's our goal. We will try to find a circuit that can make VDS1 to this value, and then also we need to set this VB to this value. So our goal is to reduce VDS1 this point intentionally by VTH. So this would be maybe our preliminary thinking that what if we use this circuit? First one is that we want to reduce the VDS here, right? So if this R1 and IREF met this condition, then VDS1 will be, so here this would be VDS1 would be VG, well, let me just write it down in blue color. So VDS1 would be VGS1 minus IREF R1, which means VGS1 minus VTH. And this is what we want, right? Because this point is VGS1. But the problem here is that we're using some R1. R1 is a problem because we at the very beginning we assume that we do have some golden IREF. We have some golden I reference, so this is fine. We can assume that this IREF is an accurate value, but this R1 is a problem. We have PVT issue. So for example, the resistor in terms of, so P was process variation. Process variation means TT, or so it's like process means TT or FF or SS. So basically these represents a NMOS and PMOS, but also the resistor has corners. Resistor has T corner, F corner, like S corner, so their value is different. In like TSMC library, the variation of resistor is like 30%, like worst case. So, and then also the resistance changes over temperature. So R1 is not accurate, so R1 is problem, and then R1 is R1 varying, so that's a problem. And there's the other problem too, VTH, this is also changing, right? So R1 is a problem, and then also VTH1 is problem. And VTH also varies. And this one is the other second issue, second thing that we have to solve. So let's assume that we somehow set this value as somehow we set VDS1 as VGS1 minus VTH. Just assume that. Then we need VB equal VGS3 1. So how do we make this? The first issue was to set a VDS1 equal to VGS1 minus VTH, right? And then since resistor has some PVT issue, we try not to use resistor. So let's look at this circuit. And then let's say here is A, and then here is X. So the assumption is that if we set VB properly, we can make VA to VGS1 minus VTH. So again, we need to find this VB, and then we will talk about it later. So assuming that we already have VB, if that's the case, we can use this schematic. But as I said, we want to put every MOSFET in saturation region. So first, let's look at the MOSFET 0, M0 saturation. What we need is VB and VTH should be smaller than VX, right? But Vx is VGS1. So it turns out VB should be smaller than VGS1 minus VTH. And M1 should be also saturation region. For M1 it should be Vx minus VTH, because Vx is here and then this is VGS1. So VGS1 minus VTH should be smaller than VA. Oh, and then Vx was VGS1, VGS1 minus VTH. And VA is VB minus VGS0, right? Because here is VGS0. So it gives us that VB should be larger than VGS1 minus plus VGS0 minus VTH. So we need these two conditions. If we merge those two, VB should be larger than VGS1 plus VGS0, should be larger than VGS1 GS0 minus VTH. Right? And it should be smaller than VGS1 minus VTH because of this equation. So it turns out if we focus on these two, it gives that VGS1 plus it should be smaller than VGS1 minus VTH. So if we remove this, VGS0 should be 2 VTH. So this is our condition. We need to properly set this transistor size so the VGS0 can be smaller than 2 VTH. To do so, what we need to do is small W0, small L. Not small W0. We need small L. So because this M0 also has to flow this IRF. To do so, we need to reduce VGS0, right? And we can have small L and then large W. So it's like large W. I mean properly. We need to properly set those two. So we're not using resistor to set the voltage A like lower, like to set this here. But we still have things to do. We need to generate this VB. By the way, so VB, we desire VB low, right? Because if VB low, then we can have more headroom here. So we can set VB as this voltage. So maybe we can put some margin, but basically this is our target. So now let's look at how can we set VB to this condition. Here's a first way to generate VB. We now have this new branch. we're using one more IREF and another current mirror. So our goal here is VB should be equal to VGS 0 plus VDS saturate, VD saturate 1. Let's see what it means. It's here first. Here's VGS 0, and then here is VD set. As we discussed before, the thing we have to do is we need to set this voltage low, right? So in this case, VD set 1 should be VGS1 minus VTH. This is what we want. This is at the edge of saturation, to be easier in the first cascode, in just normal cascode. Normal cascode, it was VD, S was VGS, and then we don't want it, right? That's why we start all of this calculation in normal cascode. VDS was VGS, and then we don't want it. We want to reduce that value, and which is here. So that means we can rewrite it as VGS 0 as VTH plus VD set 0 plus VD set 1. This is simple. The reason why we can represent it like this, because we assume that M0 is at our saturation edge. So and that comes from because for M0, VGS 0 minus VTH 0 should be smaller than VDS 0. That's what makes it saturation. So I just replace VGS 0 to here. So this is our goal. We need to make this one. In the previous slide, we set our goal that we want to make this VB to this value, and here the assumption was all of the WL are the same to make this analysis easier. And then I also mentioned that for the cascode MOSFET, we tend to make L small. But in this case, let's just assume that all the same. And then here, to make it clear, VD set 0 means VGS 0 minus VTH 0. And VD set 1 is VGS 1 minus VTH 1. Interestingly, if we set the size of M5 as 1 over 4 W over L, then we got this some value here. VB is of course VGS5, right? This is obvious. And V, as I said here, VD set 5 is VGS5 minus VTH5, right? So it becomes this. And then we want to get this part. We will do some little calculation. So here IREF is 1 over 2 mu n COX and W over L, and this would be 5 and VB minus VTH square. Let's assume VTH all the same here. So it is that if we do some math, VB is equal to VTH plus IREF divided by 1/2 mu n COX and WL5, right? We get this value. But it turns out, since this one is W/L 1/4, right? So it becomes 2 W/L, let's say just 1. Everything has, let's say just 1. All the same. M0 to M3 has all the same W and IREF. And it turns out VTH plus 2, this value corresponds to VGS minus VTH, right? Which is VTH plus 2 VD set. So, this is our results. By setting this size, we kind of got, so this is not exactly the same because VTHs are different, VGS are different, but just assume they're all similar value. So we got a this value around. We're not using any resistor, so these are all kind of matched. I mean, these are PVT immune. So we can use this, but to make it we need some margin, right? To have this, we are just at the edge of saturation. So what we can do is, if we do with some margin, we can set M5 as 1/5 W/L, something like this. Here's a second way to generate VB. By using this circuit. You note that we're using a resistor again, and then we discussed that using resistor to generate some voltage is not good because of the PVT variation, but this case is a little bit different. I will explain why later, but let's just start. So what we want VB should be, well, let's start from VA. Our goal is that we want VA is VGS1 minus VTH1 here. We don't want this voltage too high, because if we make it in the previous, if we make it as a diode connection, the VDS and VGS become same, and we're wasting VTH. Let me just brought it up again. So if we use diode connection, then VGS is equal to VDS, but what we want is VGS minus VTH, VDS. So we're kind of wasting this amount, right? Which means VDS can be lower than not here. VDS is too high in this case if you use diode, so we don't want to use it. So we want this voltage A is less than VGS by amount of VTH. So if the voltage of VA is this voltage, this M1 is the edge of saturation, right? So it gives, so VB is VA plus VGS 0, which is VGS 1 plus VGS 0 minus VTH 1. This is our target to make our desired VB. And let's see this side. So the output actually would be VB is VGS5, which is here, plus VGS6 minus I1RB. This is what we got. So we want this and this are similar. So first we can assume that first let's set, so properly design the circuit. So VGS5 is close to VGS0. If we do that, these two equations, the VB becomes VGS0 plus VGS6 minus I1 RB. So we need to compare these two again. Then it gives VGS1 minus VTH1 should be close to, well, actually our condition will be VGS6 minus I1RB should be larger than this part, VGS1 minus VTH1. So we set this I1 and RB as around VTH1, and then also VGS6 as around this VGS1, the value. So we can design this thing and then met this condition. If we met this condition, then with this M0 and M1 are in set. So if this is larger than this, then it gives more margin, like it's more saturation. So we just, if we set exactly the same, then we are using, we're fully utilizing the headroom. So now let's come back to the question that we have at the very beginning, in the previous slide, that this circuit, the new circuit, use RB to set the voltage, but it's kind of okay, but why this isn't okay? So this was our, so I raised a concern, right? So they're kind of different. In this case, R1 IREF supposed to be like VTH, right? And the point here is that our goal of this circuit is that we need to make this voltage the same. So our goal is we need to make this voltage the same. That's our goal, because we want to set the, we want this current from here, the M1 current and M2 current are the same. So we need to set them as equal. But to make it equal, we need to, but there is a process variation. It's not easy to make it equal. But this one is a little different. In this one, our goal was larger than VGS1 minus VTH1. So it's not equal. I mean, if you make it equal, then it's good because we can fully utilize the headroom. But we don't have to make it equal. We can put some margin here. So in here, we have to set this value like above something. It's the range is much relaxed than this. In this point, in this part, we have to make this voltage the same, but this part we have to use this resistor and make the voltage of this is larger than this. So it's a lot relaxed. And here, since these two are using the same MOSFET, the voltage here, this voltage A and B, this voltage VA and VB are guaranteed. So again, this circuit use resistor to set some voltage, and this circuit also use resistor to set some voltage, but this is not good, this is good, this is okay. This is not good because the goal here is we want to make the drain voltage of these two MOSFET the same. So it's kind of hard to achieve because of the PVT variation. But in this circuit, our goal is to make this voltage larger than this. We don't have to make it exactly same. We just want some range. So it's much relaxed condition to achieve. So even if there is PVT variation, we can still manage this condition. And as I said, in this case, we have to make these two voltages the same. In here, we have to make the voltage VA, VB the same, and these are automatically achieved because we're using a same MOSFET here. And there's third way to generate VB. And let's bring up the condition for VB. It was VGS1 plus VGS0 minus VTH 1, right? But it also, we can represent it as like VDS1 plus VGS0, right? Because here is, this is VDS1, and then if you plus VGS0, right? So this is our goal, And let's see this part. VB is VGS6, but we can also represent it as like VDS6 plus VGS7. So the two condition can be represented as like these two will be, the goal is like the minimum, so VDS6 plus VGS7 should be larger or equal than VDS1 plus VGS0. So we need to meet this condition. So they are kind of one-to-one mapped, right? We can set this VDS6 for this properly, so we can like similar to VDS1, and then also we can choose this GS7 to this VGS0. So like properly set the design, we can achieve this goal. And this is good because all of them are using the NMOS, not resistor. So it's kind of immune to PVT too. So here's a summary. We learned about current mirror. First, we show the concept, the current mirror concept, and then why we need that. And then we see the problem with the very basic current source, current mirror, which was just this. So the pros, I mean the limitation of this is that this voltage, the VDS, like let's say this is M1 and then this is M2, VDS1 is not equal to VDS2, so that's a problem. That was a problem. So we use current mirror. We decided to use current mirror, and then now it becomes this. We have a cascode current mirror, and then we have like this. But the problem is that the headroom. So here VDS mismatch was a problem, and here headroom was a problem. So we discussed about several circuit that can make low voltage cascode mirror, and then it basically looks like this, and it goes here and this. And here's I out, and here is I ref, and here's VB, and then we use some several circuit to generate this VB.